Hello physics students, this is Dr. Berenzi and this is a video on lesson 5.7. Just want to give you an example of how to solve problems involving collisions in two dimensions. So for my example, I have two hockey pucks, hockey puck A, which is traveling toward the right at 5 meters per second, and it collides with an identical puck B, which is stationary initially. And what happens after the collision is that one of these, the original puck, puck A, travels up and toward the right at a speed of 2 meters per second, and it has an angle of 30 degrees relative to its original direction. And then puck B moves at an unknown speed at an unknown angle, and we're being asked to find both that speed and that angle. And in this problem, we can also assume that each puck has a mass of 0.1 kilograms. Now, this is a collision, and we know that there are no external forces, or actually the net external force acting on each puck is equal to 0, and therefore momentum is conserved. And in our last unit, or in this unit, we worked with a conservation of momentum along one dimension, but now we have momentum in both x and y. It looks like a more complicated problem, and it kind of is, but it just involves more work. The principles are very similar to collisions in just one dimension, but there's an extra little twist that causes us to have to do quite a bit more math. So I'm going to actually talk to you first about the strategy we're going to use, because we're going to be ending up doing a lot of math here. So the strategy behind two-dimensional collisions is, first, you want to break down the momentum of each object into its x and its y components. So we have before the collision and after the collision. We have puck A, and it has a certain momentum, and we want to break that momentum down into its x and y components. We have puck B before the collision, and it also has an x and a y component. And so we're going to have to break down this into its x and y components, and we're going to have to break down this momentum into its x and its y components. Now, the before scenario is pretty trivial because we only have momentum in the x direction, but the math gets trickier. Well, not trickier, just more tedious when we get into the after scenario. So this has momentum in both x and y, so we would have to find the x component of that momentum and the y component of that momentum, and then we would have to find the same for puck B after the collision. We'd have to find its x component and its y component. So that's what I mean by breaking down the momentum into components. We have to find each of these components before the collision and after the collision. So that's going to involve some work. But it's not something I don't think you will find overly difficult, just tedious. Then after that, we are going to use conservation of momentum in just the x direction. So the principle behind conservation of momentum in two dimensions is that you can split everything into x and y direction and then treat each direction as conserving momentum in that direction. So I can use conservation of momentum in x, and then I can use conservation of momentum in the y direction. Now when I do these two steps here, I am going to end up with two equations and two unknowns. So I'm going to end up with a system of equations that I am going to have to solve in order to find the variables that I'm being asked for. So that's the solution strategy. Break down the momentum into components, use conservation of momentum in x, then conservation of momentum in y, and then we're going to solve the system of equations. All right, so let's get started with step number 1 here. So what I like to do is I like to keep x and y separate. So I like to create, I like to divide my paper into 2 parts, left and right. And that just reminds me that I need to keep x and y separate. So let's talk about the x direction before the collision. And then we'll fill in the y before the collision. All right, so puck A, it's pretty easy to figure out that its x momentum is just mass times its velocity in the x direction. And since it has a velocity in the x direction of 5 meters per second, you multiply those two together and you get its momentum in the x direction. You can do the same thing for puck A in the y direction, but it has no momentum in the y direction, so we know that its momentum before the collision was 0 in the y direction. And then for puck B, it was really trivial. The momentum of that puck in the x direction is 0, and the momentum of that puck in the y direction is also 0. Okay, so I've figured out the momentum in the x direction before the collision and the momentum in the y direction before the collision. So I've taken care of everything before the collision. Now I have to erase this, but you will probably just want to continue this chart right down below this if you're writing this on a sheet of paper. So don't erase this, but I'm going to erase it on my screen here. And now what I want to do is I want to look at the scenario after the collision. And I want to figure out, okay, let's take a look at puck A first. So puck A was traveling up and toward the right at an angle of 30 degrees with respect to the x direction. So I can create a right triangle and break this down into components. I think that that's going to be pretty straightforward for all of you. And then that means that its momentum in the x direction is its mass times this x component of velocity. So I'm going to take mass times this thing and get this for momentum. And that turns out to be 0.175 kilogram meters per second. And I can do the same thing for that puck in the y direction. It's just mass times velocity in the y direction. And that component is 2 times sine of 30 degrees for the velocity. So I multiply that times its mass. And that turns out to be 0.1 kilogram meters per second. Okay, so that's puck A. Now I have to take a look at puck B. And I'm going to have to erase my little diagram here and create a new one. Okay, so this one, I'm going to do the same thing. I'm going to enclose it in a right triangle. And notice that the y component now is negative since this is going down and toward the right. So make sure that you include a negative sign there. And the x component. And so the momentum of puck B in the x direction is just the mass times the velocity in the x direction, which is this. And I can do the same thing for the momentum of puck B in the y direction. So I'm going to multiply mass times this component. And I'm going to get this. All right, so I've split up the momentum into its components after the collision as well. Okay, now what I want to do is I want to set up conservation of momentum in the x direction. So what I like to do is under each of these, under x, I like to write a little before and after column. And remind myself that if I take the momentum from puck A and the momentum from puck B, I get the total momentum before the collision. And then if I do the same thing after, I get the total momentum after the collision. And then conservation of momentum says that I can set this equal to that. Okay, so I'm going to replace these with the numbers that I came up with in the past couple of slides here. So before the collision, we had a total momentum of 0.5 kilogram meters per second. And after the collision, we're going to come up with an expression. So by using conservation of momentum in the x direction, I am going to end up with an equation. 0.5 equals 0.175 plus 0.1 VB cosine theta. Okay, so that is step 2 from my solving strategy. Now I'm going to go on to step 3, where I am going to do the same thing for momentum in the y direction. So I'm going to set up a little before and after table. Find the total momentum before the collision and the total momentum after the collision, and then set the two equal to one another, and come up with another equation. So let's replace these with the numbers we came up with. So the momentum of each of the pucks before the collision was 0 in the y direction, so that is going to equal 0, the total momentum before the collision. And then after the collision, puck A had a momentum of 0.1 kilogram meters per second. And then I came up with an expression for the y component of puck B. Add those two up together and I get this expression. So my second equation that I can solve is this equation right here. Okay, so now I have completed step number 3 in my problem solving process. And now I can go up to step number 4, which is to solve this system of equations. So I'm going to rewrite these in 2 different colors, those same 2 equations that we just came up with. And what I want to do is I want to rearrange these so that I get VB times sine theta by itself. And then I'm going to do the same thing. I'm going to get VB cosine theta by itself for this equation up here. And when I do that, I end up with this equation. So I've just simplified this to solve this for VB sine theta, and I get VB sine theta equals 1. And then solve this one for VB cosine theta, and I get 3.25 is equal to VB cosine theta. Now, this doesn't look like it's something that we can solve by using elimination. You could use substitution, solve each of these for VB, but there's actually a neat little trick here. You could actually use division to eliminate VB. So let's take the first equation and then divide it by 3.25. Now, you're used to saying, well, if I divide this by 3.25, I have to divide that by 3.25. And that's absolutely true. But this equation tells me that 3.25 is equal to VB cosine theta. So I can replace 3.25 with this VB cosine theta. So I take the first equation and I divide it by that second equation. And now I've actually created a new equation that eliminates VB. So when I do that, these VBs will divide out. And I'm left with 1 over 3.25, which is equal to 0.308. And on the right-hand side of the equation, I now have sine theta over cosine theta, which is equal to tangent theta. So I solve this for theta, and I get 17.1 degrees. And now I can plug this angle into either of these equations, either that one or this one. I chose to use this equation because it looked more straightforward. And when I did that, I found out that VB has to equal 3.4 meters per second. So those are the 2 unknowns that we were being asked for. And it looks like that's the solution to this problem. So it was a lot of work. It's a lot of math, but if you understand the overall strategy, it's not all that hard to go through the steps. So, just to remind you, first of all, break all your momentums down into components, into x and y. Then use conservation of momentum in x, use conservation of momentum in y, and then you're going to solve the system of equations you came up with. All right, AP Physics students, I hope this video is helpful for you for the homework, and I look forward to seeing you tomorrow. Bye.